Look at your hand right now. Hold it up in front of your face. Look at the lines, the texture, the way light wraps around its curves, with absolute certainty that it is there. You can feel the air on your skin, maybe the weight of your phone or the warmth of a cup of coffee. This experience, this immediate and undeniable sensation of reality, is built on a foundation so obvious we never question it. That foundation is distance, the space between you and this screen, the inches between your fingers, the miles to the nearest city, the incomprehensible light years to the nearest star. It all seems so fundamentally, self-evidently real. It's the canvas on which the painting of the universe is drawn. But I want you to pause just for a moment and let a truly unsettling question creep in. A question that, if you sit with it, has the power to unravel the very fabric of common sense. What if that canvas is an illusion? What if the distance you just measured with your eyes, the space you navigate every single day, isn't a fundamental property of the universe, but something else entirely, something we've completely misunderstood? This isn't some abstract philosophical musing to pass the time. This is a question that has gnawed at the deepest minds in physics, and the clues they've uncovered point to an answer that is so strange, so counter to every instinct you have, that it feels like a magic trick. But it's not magic. It's a deeper reality. And the path to understanding it begins not with a telescope, but with a simple, playful, and profoundly brilliant line of questioning, the kind that defined one of the greatest scientific minds of the 20th century. Let's start with something familiar. When you look at the night sky, what do you see? A vast, three-dimensional dome dotted with points of light at different distances. You instinctively perceive depth. That star is closer. That one is farther. We are taught from birth to see the world in 3 dimensions. It's the grammar of our reality. Length, width, height. These are the 3 axes we navigate, the 3 directions we can move. We call it space. And for centuries, physics treated it as a silent, empty stage where the drama of matter and energy played out. Things existed in space. Space was the container. But then a young Richard Feynman, a man who looked at the world with the unjaded curiosity of a child and the razor-sharp mind of a genius, began to play with a different idea. He wasn't satisfied with just accepting the stage. He wanted to understand what the stage was made of, and he had a knack for finding the cracks in our most comfortable assumptions. He would ask questions that sounded almost childish, the kind you might dismiss before realizing they expose a profound chasm in our understanding. So let's play a Feynman-inspired game. Forget everything you know about space for a moment. Imagine you are a 2-dimensional being, a flat creature living on the surface of a vast, perfectly flat sheet of paper. Your entire universe is that plane. You can move forward, backward, left, and right. For you, distance is real. It takes effort to slide from one point on the paper to another. You can measure the inches between your flat house and your flat friend. Now imagine a 3-dimensional being, a sphere descending from above. It touches your paper universe. What do you see? You don't see a sphere. You see a point appear from nowhere. As it passes through your plane, that point becomes a tiny circle, then a larger and larger circle, and then the circles shrink again until they vanish back into nothing. You would witness a bizarre, unexplainable phenomenon, matter appearing, changing shape, and disappearing without any visible means of movement across your world. To you, the distance it traveled in your universe was small from one point to another, but the sphere itself didn't move an inch on your paper. It moved in a direction you could not perceive. From your 2D perspective, its journey defies the logic of your space. Now here's the leap. What if our reality, our 3-dimensional space, is that sheet of paper? What if what we perceive as immense distances, the millions of light years between galaxies, is not a journey across a vast, empty stage, but merely the surface effect of a movement in a direction we cannot see? What if a galaxy isn't a billion light years away across space, but a billion units away in a different dimension, a deeper layer of reality that our senses are simply not built to detect? This is the first tremor, the first hint that distance might not be what it seems. And it's a question that Feynman, with his love for visual thinking, would have adored. He would have asked, what is it exactly that we are measuring when we say something is far away? We measure the time it takes for light to travel, but light and everything else is bound by these rules, this geometry we call space-time. We're like the 2D being measuring the circles as they grow and shrink, trying to explain the universe with a ruler that only works in two directions. This leads us to the next, even stranger crack in the facade, the one that Einstein himself wrestled with. For a long time, we thought space was smooth, continuous, and empty. You could always divide the distance between 2 points in half forever. It's an infinite regression. But in the early 20th century, we started to discover the quantum world, and everything broke. We found that at the smallest scales, reality isn't smooth. It's grainy, it's choppy. Energy comes in packets called quanta. Light comes in particles called photons. So a natural Feynman-esque question arises. If energy is quantized, if matter is quantized, then what about space itself? Is it smooth, or is it made of tiny, discrete pieces? This is where things get deeply, deeply weird. Theories that attempt to unify quantum mechanics and general relativity like loop quantum gravity suggest that space itself might be quantized. They propose a universe made of tiny indivisible chunks of volume woven together into a fabric. Imagine the difference between a smooth-flowing river and a beach made of individual grains of sand. Our senses tell us space is like the river, continuous and fluid. But at the most fundamental level, the Planck scale, a scale so small that a billion of these grains would fit inside a single proton, space might be like the beach, a collection of discrete, indivisible units. If this is true, then distance isn't a smooth, continuous thing. It's a count. The distance between you and that wall isn't an empty void. It's a specific number of these quantum grains of space. You can't have half a grain. The very concept of a distance smaller than that grain is meaningless. It doesn't exist. The universe has a pixel size. And if you zoom in past that pixel, there is no there. You hit the fundamental resolution of reality. This is a direct assault on our intuitive notion of distance. It suggests that space is not a pre-existing stage, but an emergent property, something that arises from a more fundamental non-spatial reality, much like the wetness of water emerges from the interaction of H2O molecules, which themselves are not wet. So we have two profound challenges to distance: the possibility of higher dimensions that create the illusion of separation, and the possibility of a granular, pixelated space that makes the idea of continuous distance and approximation a large-scale illusion. But Feynman, ever the provocator, would push further. He wouldn't just ask, what is space made of? He would ask the most dangerous question of all: does space even need to exist? This brings us to the most mind-bending idea of all, and it comes from one of the most successful and strangest theories in physics, quantum field theory. In this view, the universe is not made of particles sitting in space. The universe is made of fields: an electron field, a quark field, an electromagnetic field. These fields extend everywhere. What we call a particle, like an electron, is just a tiny localized vibration or excitation in its corresponding field. The field is the primary reality. The particle is a temporary event in the field. Now think about what this implies for distance. If two electrons interact, what is actually happening? Our common sense view is that there are two little balls separated by a distance, and they reach across the empty space between them to push or pull on each other. But in the field view, there are no two separate balls. There is a single unified electron field. What we call two electrons are just two distinct packets of energy, two excitations in the same underlying field. The field connects them. They are not two separate things separated by a void. They are two features of one continuous thing. It's like looking at the ocean. You see two waves 100 yards apart. You think, look at those two separate waves. I wonder how they interact across all that water. But the waves aren't separate. They are both just shapes in the same body of water. The water between them isn't empty space. It's the very substance that connects them and defines them. In this analogy, the water is the field. The distance between the waves is a feature of the water's surface, but the water itself is one continuous entity. What if our universe is like that? What if the space between galaxies is not an empty void, but a manifestation of the very fields that also constitute the galaxies themselves? The galaxies aren't isolated islands in a cosmic ocean. They are eddies and whirlpools in the ocean itself. The distance between them is just a measure of how much ocean lies between the two eddies. The separation is part of the ocean. The galaxies are the ocean. There is no emptiness. There is only a difference in the state of a single universal substance. This is where Feynman's approach to physics, his diagrammatic way of thinking, becomes incredibly powerful. He invented simple pictures, now called Feynman diagrams, to calculate how particles interact. In these diagrams, particles are represented by lines. They move, they meet, they exchange other particles, they separate. But these diagrams are not just pictures of events in space and time. They are a calculational tool. And one of the most profound interpretations of them is that they represent every possible way an interaction can happen. A particle doesn't just take one path from point A to point B. In a very real quantum sense, it takes every possible path. It goes in a straight line. It loops around a star. It goes backwards in time. It goes to the Andromeda galaxy and comes back. All of these possibilities are summed up to produce the single simple event we observe. This idea, the sum over histories or path integral formulation, completely obliterates our classical notion of a single definite path through space. The distance between A and B is not a single number. It is an infinite collection of all possible distances, all superimposed on top of each other. The particle doesn't travel through space. It explores it in every conceivable way simultaneously. The distance we perceive is just the most probable outcome of this bizarre, infinite exploration. So where does this leave us? We started with a simple, solid belief in the reality of distance, and step by step we've seen that belief dissolve. We've seen how distance could be a surface effect of a higher dimensional geometry. We've seen how it could be a large-scale illusion built from quantum pixels. We've seen how it could be a measure of connection within a single universal field. And we've seen how, at the quantum level, a single journey through space is actually an infinite, ghostly superposition of all possible journeys. The final and perhaps most haunting clue comes from a place we least expected, our own minds. Think about a memory. Think about your childhood home. You can picture it, can't you? The layout of the rooms, the color of the walls, the way the light came through the window. That memory exists now in the present configuration of neurons in your brain. The house itself might be gone or thousands of miles away, but the experience of it, the feeling of being there, is happening right here, right now, in the electrical and chemical activity of your gray matter. What is the distance between you reading this and that childhood memory? In physical space, it might be immense. In time, it might be decades. But in the space of your mind, it's zero. The memory is directly present. It is a pattern of information that is instantaneously accessible. You don't have to travel across space to find it. It's already here. This is a powerful metaphor. What if the universe itself is in some sense a kind of mind? What if what we call matter is just processed information? This idea, known as it from bit, proposed by physicist John Wheeler, suggests that the universe is fundamentally formational. Every particle, every force, every galaxy is at its core a bit of information. And if the universe is made of information, then what is distance? Information doesn't need space to exist. A bit is either a 1 or a 0. It doesn't have a location. The entire internet, all the knowledge of humanity, is just bits. And you can access any piece of it from anywhere instantly. The distance between you and that information is irrelevant. In an informational universe, the concept of here and there becomes a secondary quality, a way of organizing the information from a particular perspective. The fundamental reality is the information itself, the pattern, the relationship. And relationships aren't defined by the number of meters between them, but by their logical and causal connections. So we circle back to the Beginning to your hand, what if the distance between your hand and your eye is not a fundamental truth, but a way your brain interprets a deeper, spaceless reality? What if the universe is not a collection of objects scattered across a vast emptiness, but a single, seamless, and deeply connected whole, a quantum field, a geometric object in a higher dimension, a vast ocean of information? And within this whole, what we call distance is merely a measure of difference, of separation in state, not in location. A photon in a distant galaxy and a photon in your eye are not separated by an ocean of emptiness. They are two different ripples in the same cosmic pond. The journey of that light taking billions of years to cross the void is not a journey across space, but a process of change within a single unified system. We are so used to the feeling of separation, the space between us and the ones we love, the distance to our goals, the emptiness we sometimes feel inside. It all feels so real. It defines our loneliness and our longing. But what if the deepest truth of the universe is that separation is the illusion? That at the most fundamental level, everything that ever was, everything that is, and everything that ever will be is right here in this single eternal moment of existence. You are not a lonely observer in a vast, cold cosmos. You are an expression of the cosmos itself, and the stars you gaze at are not distant points of light, but other thoughts in the same mind. The question, what if distance in space isn't real, stops being a question about physics. It becomes a question about us, about what it means to be a human being, conscious and aware in a universe that might be far more intimate, far more connected than we ever dared to imagine. And the most profound realization, the one that leaves you sitting in a quiet kind of awe, is this: the distance between you and the answer to that question might not exist at all. It was never a journey to be made. It was only a realization to be had. And perhaps, just perhaps, you've already had